Welcome to EC 5201. This is Linear Systems class. I'm going to hand out the syllabus and let's talk through these. I want to kind of explain how you get the grade in the class and what are the materials that you're going to cover in this class. Loaders, I just have one, so grab it from there. All right, so this is, let me know when you all have it. So the vital information about the course is given on this syllabus. Let me just go quickly through it. The first section here relates to me. This is my name, email, phone, room, and room in engineering building where my office is. The most important things are two last items. First one is office hours. I hold office hours Tuesday, Thursday, 2 to 5, and during that time I'm guaranteed to be in the office. You can come ask me about this course, also about any, I advise a lot of you, so all the advising matters and even any kind of matters related to the curriculum, degrees and so on. The last one is the most important. This is the location of the website that I maintain, where I post all the materials related to these classes and this class and other classes that I teach. Now, what you will find out right now on this website are the copies of all my notes, right? Everything that I use to teach the class from is already posted there. I see that a lot of students find it useful to print some of these in advance to class, and that way you don't have to take the notes in the class. You can kind of follow and fill in some of the blanks that where I say something that's not really written on the notes itself. Starting of this semester, I'm going to be posting the videos of these notes. So Masoud here is recording all the lectures, and these videos will appear on the website after, not immediately, but maybe within a few days of the lecture. This is extremely beneficial for people who travel or for whatever reason are not able to make it into the class. So you can go there and you can see what was actually covered in the class. And a lot of times it's more convenient because you can sleep in the class and eat in the class and, and stop the instructor and do all sorts of things, right? But I find it really useful and I'll try to accommodate that. So videos are going to be posted there as well. This is for 2012. There are 16 weeks in this semester, and I'm going to be using 13 of those weeks for lectures, so there will be 26 lectures in this course, and I'm going to use 2 full weeks for midterm exams and 1 week for finals. So there are going to be 3 examination weeks. When there is an examination, we dedicate a full week to examination. There are 2 class periods. One of them I'm just going to be doing some example problems here, and the other one is the actual exam. The textbook for the course is this one here. It's by Lati. I used the 2nd edition, and it's an excellent book except for its size. Right? It's very bulky and heavy, but it's a very good book. It has tons of examples. It has a lot of exercise problems. Dr. Lati writes phenomenal, right? Reading his books is like reading novels or something. It's really, really easy to read. So I highly recommend it. Nothing that I say, or very little things of what I say, will be outside of this book, right? And even the best instructor is worse than worst book. So book is always better than any instructions, and I suggest you spend a lot of time with it. There are several objectives of this course. This is one of those courses that belongs to fundamentals of this area. It is not dealing with any particular subject, but it's dealing with all subjects. It covers the mathematical tools that are going to be used by you in all of the other subjects. Going from here into DSP, you're going to be using a lot of this material. Going into communication systems, you're going to be using all of this material. Going in pretty much every one of the areas that we cover on the graduate level are going to use more or less the material from this course. So by learning it here in one spot, you actually benefit across all the courses that you're going to be taking as a graduate student. My objective here is for you to master this material on a mathematical level, making sure that you understand all the math involved here. Also, I would like you to encourage you, I'm not going to really force it in this course, but I encourage you to use this course as a kind of motivation to learn MATLAB. MATLAB is a simulation package that we use here extensively, both on the undergraduate, but even more so on the graduate level. Linear system theory is the perfect settings for that. So I'm going to be giving you a lot of problems. My suggestion is to get a copy of MATLAB and try to solve those problems. Use these linear systems as a motivation to learn MATLAB. The outline of course is given here. I'll try to stick to it as close as possible. What you have here are the areas that I plan on covering. Also how many lectures and what chapters are going to be covered. So it's really, really beneficial when you have a good book because you can kind of follow the way how the book is written. But you can see we're going to be dealing with the signals in a continuous and discrete domain. We're going to be analyzing these signals both in a time domain and a frequency domain. And we're going to finish by looking at the space-state model of a linear system, which is kind of fundamental for all the modern control systems and also filtering approaches. The credits section here tells you how you get the grade. There are 3 components to the grade. There are 2 midterms and a final exam, 30 points for each one of the midterms and 40 points for the final. That makes it 100. And then here's the scale, which is a regular scale, how you get grades. There's plenty of points, there's plenty of opportunities, so I expect that most of you are a very good grade in this course. One comment, you notice there are no homework assignments here. Usually in courses I teach, I give component of homework assignments. I'm going to be giving homeworks from the textbook. So I'm going to be giving a lot of homework problems, and they're going to be used, they're going to be the same kind of problems that I'm going to be giving for all of these midterms and the finals. As a matter of fact, what I did previous time I taught it, the actual problems that were given for homework are the ones that I used to select for the midterm exams. So in a way, you know what is going to be in a midterm exam, but don't get fooled because there's like more than 100, between 100 and 200 problems. So if you do all 200 problems, you're guaranteed to do all the problems that are in the pool for the exams. Are there any questions at this point? Go ahead.
So will there be any projects based on that?
No, not for this course. I give that in the filtering and all the other, some other courses that I teach. But here's what you need to, you're at the graduate level, so here's how you're going to treat your homework assignments. Treat every one of those as assignment, like a work assignment. And what that means, before you go to your boss, you never go with the first draft, right? You always double check it, even triple check it with somebody else, and then you present it as a solution. So you already have 2 means of checking it. Do it longhand, manually, and do it using MATLAB. If those 2 give you the same results, it's a good chance it's correct, right? But if they're different, that's your chance for learning, right? Which one is wrong? And then by figuring out why are they different, and what's the issue at hand, this is where the learning occurs. So just use MATLAB as your best friend, as something that will verify the accuracy of what you have kind of solved manually for
What if you have classes during your office hours?
Then you just send me an email and we'll meet in alternative time. Right. I'm there a lot of times. It's just that I make a point that during these 3 hours, I'm always there, right? But I'm there many other times. Just send me an email so that I don't drift away. Any other questions? All right, so let's get going.
Quick question. If we have a conflict with midterm,
Well, what do you mean conflict?
well,
with it?
you know, I don't know, most people work here, I do, so if I'm away on business trip, how do we resolve that?
Well, I'm going to try to give the dates for midterms well in advance so that you can manage that. If that happens, then we'll deal that on the individual basis, right? So let's see that. Let's see if we can manage that before it happens. Okay, so let's go and start talking about the material here. We're going to be talking in pretty much. We're going to be. Oh, first thing I write is wrong, right? Signal. There are two things that we're going to be talking about. One is the signal and one is the system. Let's first define what do we mean by signal. Signal in this course is going to be function of time. You can make it more general and say function of independent variable, and that makes sense because like if you talk about image, there is also motivation to introduce a spatial coordinate. But in this course, we're going to limit our attention to signal as a function of time. We're going to be using notations like x of t, indicating that this is a signal x as a function of time. And it can be this signal can be of many different qualities. It can be continuous, it can be discrete. Maybe discrete, in maybe analog, digital, and so on. So there are quite a few attributes that we can attach to this signal. We're gonna, in a particular spot in the course, define what we mean by each one of them. But we're starting from a very general category where anything that is a function of time can be understood as a signal. We're going to define several attributes of the signal. First one that I'm going to define is the signal energy. And we define the energy of the signal, let's say in the notation Ex, as an integral from minus infinity to plus infinity, magnitude of x of t squared dt. So that's essentially area under the magnitude square of the signal. If we have two cases, one case is when x of t is real, meaning that at any instant of time, x is just a single real number. And in this case, energy of the signal, E of x, can be written as integral from minus infinity to plus infinity, x squared of t dt. Notice I have just removed the absolute value and I'm just squaring the number, because the square of the real number is the same of the amplitude of the real number squared. Now, in the case of in the second case, x of t may be complex. In this case, x of t is represented at any given time, is represented as two numbers that travel in pair. One of them is the real part, the other one is the imaginary part, j is of course square root of minus 1. So for complex signals, that's we have two signals, two real signals that are traveling in pair. In this case, energy of the signal is calculated minus infinity to plus infinity. Again, definition is x of t squared dt. But when I substitute, this is minus infinity to plus infinity, magnitude of x of t, x real of t, plus j, x imaginary of t, magnitude squared dt. We compute this as integral minus infinity to plus infinity. How do we calculate the magnitude of the complex number? It's real square plus imaginary square. So it's going to be, and then square root of that to get the magnitude. So the square root will be eliminated by this square here, and we end up x r of t squared plus x I of t squared dt. So that's a power energy of the complex signal. So if the signal is complex, its energy is sum of the energies in the real part and the energy in the imaginary part. The signals that have finite energy, the signals for which energy is finite, are called energy signals. Okay? So if I take a signal and I take its magnitude and then I square it and then I integrate the area under the curve over the entire t-axis and I get a single number, now something that is finite, then I call that signal belongs to a class of signals that are energy signals. Most of the time in practical situations, the signals that are finite in duration are energy signals, right? That's like a rule of thumb. If you have a signal that lasts for a certain amount of time, then this is an energy signal. Typically, in digital communications, we talk about energy signals because one bit or one symbol is localized in time and its energy is finite. The second definition that we're going to use for signal is the signal power. So, signal power. The power of the signal is defined as a limit when capital T goes to infinity, 1 over t, integral over t, x of t, magnitude squared, dt. We kind of start similar here. We're taking the signal, it's taking its magnitude, squaring it. We're looking the area under the curve, but what is the difference here is we're looking it into within an interval of the length of the capital T, and we are dividing by the length of the interval. So if you think about it, what this represents is power is the average energy averaged over time, right? So again, we have two cases where x of t can be either real or complex. So if x of t is real, then I have the power of the signal is limit when t goes to infinity, 1 over t, integral over t, x of t squared dt. For real signals, I can eliminate this magnitude here because the just squaring it is the same result as taking the magnitude and squaring it. And for complex signals, x of t is complex, i.e. x of t is equal to x real of t plus j x imaginary of t. When I substitute that into this expression here, I get that the power of the signal is limit when t goes to infinity, 1 over t, integral over t. Now x real of t plus j x imaginary of t, magnitude squared dt. And following the same approach as I did for the energy, this becomes limit when t goes to infinity, 1 over t, integral over t, x real squared of t plus x imaginary squared of t dt. And you can see that this splits into two integrals, each one of them having a property of the power. So the power of the complex signal is the power of the real part plus power of the imaginary part. So just like in the case of energy, you get that in the complex case, the energy and the power are sum of the energies and the powers in a real and imaginary part of the signal. So just a kind of informal view. Actually, before I go there, let me just summarize here. Signals with finite power are referred to as power signals. Okay, so how does typical power signal? Let's look at two typical signals here. This is how an energy signal might look like, right? So this is energy of the. I mean, it doesn't have to be. It doesn't have to be this way. The strict definition is given here, but if you look at this signal and it's localized in time and it kind of dies after a certain time, this is an energy signal. Intuitively, you can see that if you square this and take the area under the curve, you're going to get a single number, right? Energy of the signal. The power of the signal, the power signal kind of goes for a long time. You can see that its area under the curve is infinite. If I take this signal and sum up the area under the curve, it's going to be infinite. But the average of the energy per unit time is going to be finite. So the power of the signal is finite. Signals can be either energy or power, cannot be both. So if you look at the signal, it's either energy signal or it's a power signal. And you can see if the signal is an energy signal, what is its power? Zero power. And if the signal is a power signal, what is its energy? No? Infinity, right? Be careful. So if the power signals have infinite energy and finite power, energy signals have finite energy and zero power. Okay? So let's walk through some examples and illustrate calculation of these. I'm going to look at the power of a few signals. So this is the same as example 1, 2 in your textbook. It says determine the power of the following signals. And I have 3 signals. First one, x of t, is c cosine omega 0 t plus theta, where omega 0 is different than 0. Signal B is x of t is c1 cosine omega 1t plus theta 1 plus c2 cosine omega 2t plus theta 2, where omega 1 is different than omega 2, different than 0. And both of these, as you can see, are real signals. And in part 3, the signal is d e to the j omega 0t, if this is a complex signal. So let's first determine the power of the first guy. Now, the power is defined as a limit when t goes to infinity, 1 over t, integral over t, the magnitude of the signal squared. So if I take the magnitude here is squared, is c squared cosine squared omega 0 t plus theta 0 t. So what did I do? Took the first signal, squared it, and I put it inside this integral here, and then I'm integrating over a period of the length of a time that is t, and I'm dividing everything by time to get average energy per time. So now, what can you tell me about this signal cosine? We know that this is a periodic signal. So interpretation of power is average energy per time. So intuitively, you can see that it's enough to look at one period, because whatever is the average over one period holds over entire signal. Why? Because the periods repeat. So the average here, you know, all the averages are the same. So instead of integrating over this t that goes to infinity, I can actually divide everything, integrate everything over the period. The period here, t0 is 2 pi over omega 0. So I can say that the power of this signal is 1 over t0, integral over t0, c squared cosine omega 0 t plus theta 0 dt. And this can be simplified. This is 1 over t0, integral over t0, c squared, 1 plus cosine 2 omega 0 t plus theta 0, everything divided by 2 dt. What did I do here? I used the trig identity. This square missing here. So we put it here. That we're going to use quite a bit in this course and other courses, that cosine square of x is 1 over 2, 1 plus cosine of 2x, right? And then sine square of x, just when we're here, is 1/2, 1 minus cosine 2x. These are the two trig identities that we're going to use quite a bit. You can see here that this is what I've used here to decompose this cosine square. Where is the mistake?
The true.
2 is missing. Where is it missing? In front of 2, 2 theta 0. Okay. So let me continue with over here. So in this case, this power splits into two integrals. This integral here splits into two. 1 over t0, integral over t0, c squared over 2 dt. And then plus 1 over t0, integral over t0, cosine of 2 omega 0 t plus 2 theta 0 dt, everything divided by 2. So what are the values here? Now we can do this and we can integrate, but let's think about what is it that we're doing here. This operator here, 1 over t0, integral over t0 dt, is performing the time domain averaging of whatever is inside this integral here, right? What I do here is I'm looking at this function here. I'm integrating the area under the curve, and I'm dividing by the length of this interval. So what I'm really looking is for the average value of the function that I'm integrating. So what is the average value of the c squared over 2? What's the average value of the constant? Of a constant? Constant itself, right? So the value of this integral here is c squared over 2. Now, here, I'm looking for an average value of a cosine over 2 of its periods, full periods, right? How do I know it's 2 periods? Because I'm integrating here over the period of the cosine with the frequency omega 0. So t0 is the period associated with frequency omega 0. This one here has a frequency 2 omega 0. Therefore, its period is half of the original period, right? Its period is 2, 0 over 2. So since I'm integrating over t0, I'm integrating over 2 periods. So what's the average of the cosine over full 2 periods? 0, right? So the value of the second integral is 0. So the power of the sinusoidal is c squared over 2. And we already know that this is the result that we have seen maybe in circuit theory way earlier in our schooling here. Let me define something here. Frequently, we define RMS value of a signal. And the definition is X RMS is defined as the square root of power, right? So you would define it as a limit when t goes to infinity, 1 over t, integral over t, x magnitude of t squared dt, and then take the square root of that. So if it comes to the sinusoidal, what is the x RMS in this example? It's going to be c over square root of 2. This RMS stands for root of the mean square. I take the quantity, I take its square, I find its mean value, meaning I average over time. How do I do that? Through this integral, limit 1 over t, integral over t, that's performing the time domain averaging, and then I take the root of that. So that's root mean square. That's the explanation for the acronym here. Let's look at the part B here. In this case, power is, you always start the same. Limit when t goes to infinity, 1 over t, integral over t, and then the whole signal squared. So this is C1 cosine omega 1t plus theta 1 plus C2 cosine omega 2t plus theta 2, everything squared dt. Notice I'm not putting an absolute value here because the signal is real, and therefore I can just square it, right? If this was a complex signal, then I would have to take the magnitude of what's underneath and then square the magnitude. Now, when I square this splits into 3 integrals. Limit when t goes to infinity, 1 over t, integral over t, c1 squared, cosine squared, omega 1t plus theta 1 dt. That's the first one. That's the integral over the first quantity squared. Then I have another one, which is limit when t goes to infinity, 1 over t, integral over t, c2 squared, cosine omega 2t plus theta 2. That's the integral of the second quantity squared. And then I have the cross term, right? So I have the third one as limit when t goes to infinity, 1 over t, integral over t, c1, c2, cosine omega 1t plus theta 1, and plus times cosine omega 2t plus theta 2 dt. Of course, dt is missing here as well. Now, the first two ones, we already know the answers. If you look at the first one, that's the example A, right? Because I'm taking the C1 cosine omega 1t, I'm squaring it, and I'm taking the average over time. So what's the result here?
C1 squared by 2.
C1 squared divided by 2. What's the result here? C2 squared divided by 2. What's the result here?
C1.
Okay, so let's figure. This is the only one interesting. So let me see here. Px is C1 squared divided by 2 plus C2 squared divided by 2. And for this one, I'm going to use another trig identity that said that the cosine alpha cosine beta is 1/2 of the cosine of the sum plus 1/2 of the cosine of the difference. So I have that this is plus. The first one is the limit. T goes to infinity, 1 over t, integral over t, c1, c2 over 2, cosine omega 1 plus omega 2 t plus theta 1 plus theta 2 dt. And the last one is limit when t goes to infinity, 1 over t, integral over t, c1, c2 over 2 cosine omega 1 minus omega 2 t plus theta 1 minus theta 2 dt. All right, so let's look at this integral. One of the things, and the reason why I do this in a great detail, is the attempt here is to try to integrate this, right? And then say, okay, integral of the cosine is sine, and then you're stuck. You say, well, what happens? What borders do I substitute here, right? And that's not how you evaluate these integrals. How you evaluate them, you actually think what they physically mean. This integral here is a time domain averaging of whatever is underneath this integral, whatever is the function here. So if the function is cosine, what's the time domain average of the cosine?
Zero.
Zero. So this is a pure cosine, so the time domain average of this is 0. What is the time domain average of this one?
0.
0 as well. It is not 0 in only one important case. When would this not be 0? If omega 1 is equal to omega 2, right? In that case, it would be C1, C2 over 2 times cosine of theta 1 minus theta 2. But we already guarded against that case. If you look at the beginning of the problem, it is explicitly stated that omega 1 is not the same as omega 2. So if omega 1 is different than omega 2, this is 0 as well. And we end up with a C1 squared plus C2 squared over 2. Now, this is kind of very cool that we have mixture of the cosines, and the power of the mixture is the power of the sum of the powers of the individual components. That's a very noble properties of the cosine. It is called orthogonality. Cosines of the different frequencies are orthogonal to each other. That's why the power of their sum is equal to the sum of their powers. That can be generalized, and we'll talk about it a little bit later when we start talking about the Fourier analysis. Let's look at the third example. Now we have a complex signal here. So in part C, we're looking at the power, again, limit when t goes to infinity, 1 over t, integral over t, magnitude of d e to the j omega 0 t dt squared. Now, what is the magnitude of this?
Square of the real plus square of the imaginary. And
Okay, that's one way of doing it, right? But this is, how do we call this d?
D is outside.
If I have a complex number, z, in a format a e to the j phi, how do we call a?
And that's the values.
We call it
Magnitude.
magnitude. How do we call phi?
Phase.
Phase. So here's the thing. Here's your z. This is your a, right? Magnitude. This angle here is phi, right? Right? What was mentioned before, how do we call this?
Yeah.
This is xr, and this is y. Let's call it xi for imaginary. So you can see right away xi squared plus xr squared is equal to a squared, right? So you can determine by taking real and imaginary part, but you don't have to. The magnitude of this is d, right? So this becomes easier of all the cases. This is limit t goes to infinity, 1 over t, integral over t, d squared dt. So I'm averaging d squared over time. So what's the average of d squared? Just d squared, right? So the power here is d squared. Okay. So that's the definition of the energy and the power of the signal. Let's look at some useful signal operations. Some okay. The first one that we're going to talk about is time shift. right? Usually when we talk about time, it's kind of arbitrarily defined where in all of these problems where you start the time. And then the signals may start or start at some arbitrary point relative to the zero that you have defined. So it's important for us to understand how these shift around. So let's say I have defined my time coordinate system. So this is x of t, and let's say this is how x of t looks like. This is some zero that I have chosen. Then if I shift, if I delay x of t, so x of t minus capital T would look somewhat like this. This would be a delay. So if I have here minus capital T, what that means, I'm shifting the signal right in time, right? Delay here appears with a negative sign. So it's delayed by capital T. Now, alternative to that would be signal x of t plus capital T. And this one is what? This one is advancing time. So it's shifted to the left. So this would be now capital T. And this one is advanced by capital T. So that's the first operation. It's basic. I kind of included here for sake of completeness, right? I'm sure you're familiar with it. The second useful operation that we do to signal is scaling. So let's do that one. So scaling, let's say we have a signal, again, x of t, that looks somewhat like this. Then the scale version of x of t is going to be x of a t, right? And we can have two cases here. When a is larger than 1 and when a is smaller than 1. When a is here, a is larger than 1, then you can see that this argument here grows faster than the t itself, right? So when you feed this argument into the function of x, you can see that it will go through all of these values here quicker than over here. So what that does, it compresses the signal in time. So this is x of at for a greater than 1. When a is smaller than 1, but still we allow only positive values in the scaling, then the signal is going to be stretched in time, right? Because it will take this at more time to get to a certain value than with just t alone, because a is smaller than 1. So in this case, the signal will stretch in time. So these are the two scaling properties. This one is compression when a is greater than 1, and this is expansion of the signal in a time domain where a is between 0 and 1. The third operation that we're going to do all the time is time reversal. If x of t is some signal, then x of minus t is a time reversed version of the signal. Okay, so how do they look like? So if x of t, let's say, looks somewhat like this, then your time reversed version of x of t might look somewhat easy to draw. Right? It's like a mirror image of the first one. So this is of x of minus t. Right. This one advances to the right. This one advances to the left with the t. Okay. So those are basic operations. We're going to use them all the time to represent various things about the signal. You know, shifting it in time domain, scaling it, you know, in a time domain, or performing the time reverse. So let me go through a quick classification of the signals. I have already mentioned that we start from a very broad perspective. We start by defining a signal just as a function of time. So let's, and then that we kind of can subdivide into major different categories of signals. So let's define some of these categories in more precise terms. But let me first list 5 of them here. One is signals can be continuous or discrete time. So that's the first distinction that we can have between the signals. The second, they can be analog or digital. Third distinction, we can talk about periodic and aperiodic. We already kind of mentioned power and energy. And deterministic versus probabilistic. A lot of these can go together. For example, we can talk about continuous digital periodic signal. That would make sense, right? But some of these combinations will not make sense. For example, you cannot really have periodic energy signal, right? Because that would mean that that the energy per period is equal to 0, right? So, but a lot of these combinations can coexist together. So let's use a couple of minutes here to define what do we mean when we say continuous versus discrete. What do we mean when we say analog versus digital? So let's take a look at the first classification here, continuous versus discrete. A lot of them are intuitive, but there are often mistakes are being made. For example, one of the most common mistakes is when where continuous is misunderstood to be analog, right? Or discrete is mistaken for digital. So, first division, continuous and discrete time. This subdivision of signals characterizes their behavior along the t-axis. So we are only considering t-axis. And if we look at the t-axis, there are 2 options that are possible. Signal may exist at every point on t-axis. And in this case, we talk about continuous signals. So continuous signal might look somewhat like this, xc of t. And formal definition here is xc of t is defined for every value of t, right? So if the signal exists, you know, for every value of t, then the signal is called continuous time, right? Special case, it may be 0 at some t, right? But as long as we know what it is for any given t, then the signal is continuous time. It exists over the entire t-axis. Now, alternative to that is the signal that only exists for some points on t-axis. So this is x d of t, x d of t is only defined at some instances of time. Now, that doesn't mean that it is 0 here, right? It's not 0 here. Simply, if you ask me what the value of the signal at this point is, that question has answered, it's not defined. I don't know what it is. The signal does not exist at this point. Signal only exists at discrete points in time. They can be equally spaced or not equally spaced, but important is that it only exists in discrete values of t. Some signals come naturally this way, right? If something occurs, periodically or at some intervals, but it's undefined in the meantime, then we have this kind of signal. Now let's look at analog versus digital. Now, when it comes to continuous versus discrete, we're looking at the t-axis. When it comes analog versus digital, we're looking at the y-axis. We're looking at the amplitude. So analog signals may look somewhat like this. Let's say this is an analog signal. And I deliberately kind of draw it a little bit funny, just to point the little nuances here. This is an analog signal. Why is it an analog? Because it occupies the range of values in the amplitude domain. It's not discrete in the amplitude domain. It is not continuous time, right? So analog signal doesn't have to be continuous time. But it occupies range of values. It's not quantized on the y-axis. So analog signals, let me just do it like this. X8 of t, amplitudes is in amplitude occupies continuous range. On the other hand, we have digital signals that might look somewhat like this. Right? So this is x d of t, where these values are coming from some predefined set of values. All the values in between are not possible. The signal cannot take any value in between these two. So there's discrete points on the y-axis that the signal can take. This is a continuous signal, continuous time signal, but it's digital. It is only taking discrete values along the y-axis. So the I guess x d of t takes discrete amplitude values. From this definition, you can see that all combinations are possible. You can have a continuous signal that's analog, right? It is continuous in both time and amplitude domain. It takes, a lot of signals are like that. When you look at speech signal, when you look at signals that are coming from measurements, many of them are like that. But then the signal can be continuous in a time domain, but discrete in the amplitude domain, in which case you talk about this kind of signal, and all sorts of combinations that you can create in between these categories. 3, periodic versus non-periodic. X of t is periodic if there is a positive constant t0 such that x of t plus t0 is equal to x of t for every t. Now, when you look at this t0 as a constant, you can see right away that if the signal is periodic, there are many of these t0s. If the signal is periodic with period t0, then it's also repeat itself after 2t0, 3t0, and so on. The smallest constant for which this is holding true, we call period. So the smallest t0 for which this equation here holds is called period. And then if the signal is not periodic, is non-periodic, right? All the other signals that are non-periodic are called non-periodic signals. So just okay, so let's look at the next division. We kind of talked about it already, but let me summarize it here. Energy and power signals. So x of t is signal, and we have Ex as integral from minus infinity to plus infinity, x of t squared dt. This is what we define as energy. And we have Px as a limit when t goes to infinity, 1 over t integral over t, x of t magnitude squared dt. This is what we call power. Now, if energy Ex is equal to is finite, and power is equal to 0, this is an energy signal. And if energy is infinite, but the power is is finite, then this is a power signal. Okay, all of the practical signals follow in one of those categories. They are either energy or power signals. Right? We can construct some signals, and we may actually do that a little bit, that don't fit this category. For example, if the signal has an infinite energy and infinite power, then it's not in either one of those. But those signals are not natural signals. They're mathematical constructions. Nevertheless, they may be useful, but most of the real signals that occur in practice are either energy or power signals. And the last division that I mentioned here is deterministic versus random. The deterministic signals are fully specified signals. We have no ambiguity what they are going to be at any given point in time. Right? They can be specified in different ways. The most basic way is to give a formula. Right? So if I say x of t is cosine omega 0 t, then this is a deterministic signal. Give me a t, I'll tell you what x of t is going to be. So deterministic fully specified. And as I said, you can specify it as using formula, you can specify using graph, you can specify using table, whatever may be the means. But give me the time, and I can tell you exactly what the signal value is at any given time. On the opposite end of the spectrum are the random signals. And these signals are specified only through their probabilistic measures, right? You can specify them using PDFs and CDFs. And in this case, for any given time, you're talking about probability that the signal is going to be below a certain threshold or going to be within a certain interval of the value. So these signals are specified by PDF and CDF in amplitude domain or through and through autocorrelation function in time domain. And don't worry too much if there's a little bit of ambiguity here. We're going to talk about these signals in mostly some other courses and kind of spend a lot of time dealing with them. Because if you really think these are the most important class of signals that we deal with. A lot of our communication systems, a lot of our control systems, they're actually designed to handle the signals that we don't know what they are a priori. Like for example, if you look at your voice communication systems, they're designed to handle voice. And that as a category is a random signal because you don't know a priori what somebody is going to say. Otherwise, it wouldn't be even worth putting the system together. You can just write it down at the receiver, right? So you have to design a lot of times systems to the signals that are random in both amplitude and a time domain. But in order to understand how you design the systems, you have to deal first with the deterministic systems, and a lot of times we actually test and design around deterministic systems, knowing that the random signals are going to behave similar to their deterministic counterparts. Okay, so kind of this is the first lecture, so I wanted to, most of this is review material. These are first couple of sections in chapter 1. I know you know most of this stuff, so I kind of went quickly through it. And let me give you some selected problems for this section. So it's 1.1, 1, 3, 4, and 6, 1.2, dash 1, 3, and 5, and 1.3 dash 1, 3, 5, and 6. So there are a lot of problems here, but they're all relatively easy, kind of exercising the material that I went through tonight. Any questions here? Okay, so that's it for this first lecture.